Good morning to all of you. Today we are going to learn about deuteron magnetic moment. This lecture will be based basically a theoretical estimation of deuteron magnetic moment. Any theoretical estimation needs support from the experimental measurement. So we will also learn about experimental measurement of deuteron magnetic moment. This requires knowledge of deuteron ground state, which we have derived in the previous class. Keeping that information in mind, we proceed today's lecture. I am Dr. Raghu A, working at Postgraduate Department of Physics, Government College Autonomous Mandya. This is the outline of my lecture. Let us start from the beginning. Deuteron magnetic moment is computed as the magnetic momentum due to two particles, which are the constituent particles of the deuteron, proton and neutron. So it's a vector sum of magnetic momentum due to proton and magnetic momentum due to neutron, which is shown in the equation below here. In turn, magnetic moment of proton is actually because of the orbital motion and spin motion of the particles of proton. Similarly, that for neutron also contributes to mu L and mu N. Now this orbital angular momentum and spin angular momentum, which give rise to corresponding magnetic moment, can be expressed as in terms of gyromagnetic ratios as mu d is equal to gl dot L vector L plus gs dot vector S for proton. Similarly, that for neutron. All these g's are gyromagnetic ratios. These gyromagnetic ratios are experimentally measurable, and the measured values of these gyromagnetic ratios are shown here in the form of table. For proton, gyromagnetic ratio for orbital motion is 1. For neutron, that is 0. And the other two values for the spin motions are given here. These two values we already used it in the previous lecture as well. So these gyromagnetic ratios are expressed in terms of nuclear magneton mu n. Now note that this intrinsic angular momentum for the two particles is written as half times sigma h cross. I'm not going to use h cross here, I'm going to use only half sigma here. So when we use this half sigma in this s value here, in this part and that part, we can simplify the expression in a simple manner. Experimental measurement. Keep that equation intact. Now let us denote the proton and neutron with the symbols 1 and 2, just for the simple notations. With that notation, then the previous expression becomes mu d equals vector L plus g1 dot of into sigma 1 plus g2 dot of into sigma 2, where 1 and 2 for g and sigma are respectively for protons and neutrons. Now, what is and how experimentally magnetic moment is measured? It is measured along some reference direction, and normally that reference direction is taken along z direction. Basically, that's where actually the field is applied, magnetic field is applied. So that is shown in the picture right hand side here. So in the right hand, this picture, the vertical line, blue line, which is going vertically upwards, is the direction of z, and mu is making some angle with that z. The projection of mu along z is actually what is measured experimentally. In the center of mass system, Lz in lab is equal to half times Lz in center of mass system. Using this in this equation, then we can simplify further the mu expression for magnetic moment and taking the fraction of common outside, that will be equal to vector mu z, which is basically due to magnetic momentum equals to of times Lz plus G1 dot sigma 1z plus G2 dot sigma 2z. Remember this equation, what we will be using this equation 1 again and again. So this mu z equation 1 is basically expression for experimental measurement value of magnetic moment. And theoretical estimation. How we can estimate the value physical quantity like magnetic moment? We can estimate either using classical mechanics or in quantum mechanics. Since we are actually dealing with the quantum mechanical theory, the theoretical estimation of magnetic moment is nothing but actually the expectation value of that physical quantity. Here that is magnetic moment, bracket of mu z. And this bracket notation should also associated with the corresponding wave function. We are dealing with the ground state of deuteron function, therefore this expectation value should be evaluated for ground state wave function of deuteron. Then that mu z will be equal to rho psi gs operator mu z acting on ket vector psi gs, where psi gs is ground state wave function of deuteron. So that we have already derived in the previous class, that in simple notation that is given as A psi gs plus B psi d. So using these things, magnetic moment theoretically is estimated in terms of expectation value like that, separating out the wave functions for S state and wave function for D state separately. Then we get the two parts here shown in this part here. The first part is actually for S wave function, S state wave function, mod A square psi gs mu z acting on psi s, and plus mod B square bra psi d on operator mu z acting on ket vector psi d. So these two are defined. Now consider only the first part of equation 2 here. So if you just consider that, and using equation 1 is actually the expression for mu z, the equation becomes in this form: mod A square equals bra vector part psi s, the entire operator is off into Lz plus G1 dot sigma 1z plus G2 dot sigma 2z acting on the ket vector psi s. Now, in case of S state, orbital angular momentum is 0, therefore its z projection Lz is also 0. The first term of the previous equation cancels. So then the equation simplifies in like this: mod A square psi s G1 dot sigma 1z plus G2 dot sigma 2z acting on psi s. So this I am going to separate it for the first part and two parts separately. I am calling the two parts as 1a and 1b, and calling this entire equation is equation 3. So in order to solve this particular 1a or 1b, we need to know the expression for psi s, where psi s is the S state wave function of deuteron, which is equal to radial wave function times spin angular wave function xs. So with that, 1a can be written in this manner: 1a equals rs or y00 alpha 1 alpha 2 acting on g1 sigma 1z, again acting on the vector rs or y00 alpha 1 alpha 2. The same expression is written here. What is important to note here? G1 is actually a constant associated with the sigma 1z. Sigma 1z is a spin operator. It's a matrix operator. Spin matrix operator operates only on spin wave function. And we have only two spin wave functions here, alpha 1 and alpha 2. Sigma 1z, the number 1 in sigma 1z refers only for the first particle. Therefore, sigma 1z acts only on the first particle of spin wave function. Rs of R is a radial wave function, y00 is angular wave function. They will not be octated by this operator. Therefore, that can be separated out. Note that all these wave functions are normalized. Therefore, when we do separation, we get an expression for IA like this: bracket of Rs of R, bracket of I00, bracket of alpha 2, then bra alpha 1 G1 dot sigma 1 Z ket alpha 1. All these things become 1 because their wave functions are normalized. So only important thing is the equation containing this G1 dot sigma 1 Z acting on alpha 1. G1 we can take it outside, and alpha 1 Z acting on alpha 1 gives 1 times the same wave function. So this is actually given as an exercise in the previous lecture to you. Those who have solved it, you can easily get that. So with this G1 times bracket of alpha 1 again becomes 1. Therefore IA just becomes G1. G1 refers to gyromagnetic ratio of first particle. First particle is proton. Exactly on similar lines, we can show that 1B to be equal to a radial wave function, angular wave function, and spin wave function acting on G2 times sigma 2Z, acting on again the ket vector, and this sigma 2Z is a spin operator, and that acts on only on the second wave function, spin wave function. So then with the same lines, you can show that 1B to be equal to Gz. Substituting all these values in equation 3, we get the first part of the magnetic moment to be equal to mod A square by 2 times G1 plus G2. G1, G2 values are already given. Now if we assume that a deuteron is completely made up of S state, in other words, if ground state of deuteron is a pure S state, then mod A square is 1 and mod B square is 0. Then magnetic moment for only for S state is written as mu Z of only S. So that will be given by the above expression, and substituting the value of G1 and G2, we get the result for pure S state, magnetic moment for pure S state to be mu S, which is equal to 0.87925 mu N. Remember this equation 4. This is the magnetic moment for pure S state. Now this value 0.87925 mu N is unfortunately different from the experimental value. Experimental value is 0.85735 mu N. Because of this difference, it tells that experimental values are measured accurately up to 7 decimal. Therefore, we cannot correct anything in experiment. What we can do is only we can understand theoretically how what is happening here. So this implies that the ground state of deuteron is not a pure S state. Now consider the second part of equation 1. Then if you consider that, then that second part is written as mod B square bracket of psi D for operator mu Z. Using equation 1, which is expression for mu Z, we can separate out into 3 parts, and these 3 parts I am denoting it as 2A, 2B, 2C. Remember that I am calling it as equation 5. Okay. Note that the D state wave function is again the product of radial wave function for D state times spin angular wave function for D state. With keeping that in mind and considering only 2A part of equation 5, the expression becomes like this. The first is actually bra vector is a very lengthy expression which contains a wave function for radial wave function part, and spin angular wave function part. What is important to note is that this is acting on only LZ, radial correction, angular wave function LZ. So LZ angular wave function only acts on the angular wave function. It doesn't act on the radial wave function and doesn't act on the spin wave function. So there are three angular wave function, y20, y21 and y22. How does this angular wave function acts? So now if you remember the quantum mechanics, basics of quantum mechanics, Lz operating on the angular wave function YLML gives a very standard result that gives rise to ML times the same wave function. And although it's not required, I am giving the second result also here. L square acting on YLML gives rise to square of angular momentum L square times the same wave function. These are two eigenvalue functions and eigenvalues. Very important, you must remember that. So using this information, and we can have this knowledge, okay, LZ acting on YLML giving rise to ML times YLML. So this part has only three parts containing angular wave function. LZ acting on Y20, 0 is ML value for the first part, therefore LZ acting Y20 gives you 0 as the eigen solution. That is given here. Similarly, this eigen solution for this is 1 and eigenvalue for this is 2. Those two values are substituted here, and doing simplification you get 2a to be equal to 27 by 20. This I am calling it as equation 6. Now consider equation 2b. Equation 2b is actually part containing the bracket wave functions along with this operator G1 acting on G1 times sigma 1z. G1 is just a coefficient of sigma, we can take that outside. Sigma 1z is a spin operator and acts only on the first spin wave function. So we have spin wave function here alpha 1, spin wave function here alpha 1, for first particle, spin wave function here for beta 1 and spin wave function for here for beta 1. So this sigma 1z contains only 4 parts. All other wave functions reduces to 1 because they are already normalized. So when that is simplified, we get 4 parts here along with the coefficient root of 1 by 10, and but multiplied by the ket vector become square of root of 1 by 10, which is equal to 1/10. So we have these parts here, alpha 1 times G1 sigma 1 acting on alpha 1, similarly for other parts. So if you know how to get the sigma 1 acting on the ket vector, you can easily simplify that. So that is the standard result. Easily one can derive that. Sigma 1z acting on alpha 1 gives us 1 times the same ket vector. Sigma 1z acting on beta gives rise to minus 1 times the ket vector. So because of that, this minus 1 sign we are getting because sigma 1z is acting on beta 1 here. So with this, actually this particular part will become 0, and we have to algebraically simplify 1/10 of time plus 3 by 5 of minus 1. If you do simplification, you get very simple results. 2b equals minus g1 by 2. So this is for second part in 2, and third part we can solve exactly on similar lines. That will be equal to 2c, which is again minus g2 by 2. So substituting equation 6, 7, 8 in equation 5, we get the second part of the magnetic moment. That's equal to modulus of b square by 2 multiplied by 27 by 20 minus g1 by 2 minus g2 by 2. So you can substitute the values of g1 and g2 and you can get the value of 2. What is important, if you assume that deuteron is made up of pure d state, then mod b square is 1, mod a square is 0. Then magnetic moment for only for d state is written as by this expression. So for a pure d state, the magnetic moment will become 0.2350 mu n. So this is actually equation, I'm denoting it as equation 9. Again, this value is different from the experimental measured value, which is 0.85735 mu n. This implies ground state of deuteron is not a pure d state. Also, we can assume that from these studies, magnetic moment of deuteron is an admixture of S and D state. If that is the case, then we can write mu z of experimental value as a sum of state magnetic moment modulus A squared plus B squared into magnetic momentum of D state. So we can substitute the values of this mu zd from equation 9 and mu zs for a state wave function, which is solved it in previously for and denoted as equation 4. Using those two in the above equation, we get this expression. Left hand side the experimental measured value, right hand side we have mod a square times S state value mod b square times d state value of magnetic moment. So equation 10, what we have, this is a problem. This we have only one equation and there are two unknowns, a and b. Modulus a square has definite meaning, modulus b square has definite meaning. The meaning is modulus a square gives the probability of finding the deuteron in S state, modulus b square gives probability of finding the particle in the D state. Now, how can we solve this equation with two unknowns? It is impossible to get a unique solution for such an equation. So we need one more equation. Now that can be solved again by the probability theory. There is a 10% probability of finding the deuteron either in S state or in B state, always. So mathematically that probability condition is written as modulus A square plus modulus B square equals 1, or we can simplify that to be equal to B square equals 1 minus modulus of A square. So using that, equation 10 can be written like this. Okay, so I'm just substituting the values of A square. So for B square I'm substituting B square equals 1 minus A square in the expression. The expression becomes like that, and remaining things are only algebraic simplification. You get mod A square equals 0.966. So this value we can substitute in this expression to get the value of B square. So using those two, we can actually solve for B square as well as A square. So then we can write in result like this: modulus A square equals 96.6% and modulus B square equals 3.4%. It tells probability of finding the deuteron in the ground state for S state is 96.6%, for D state it is only 3.4%. Collectively, the meaning is deuteron exists predominantly in S state and only a small admixture of this state. So that's actually the estimation of deuteron magnetic moment, and in other words, it tells also how long the deuteron particle stays in this state and how long it stays in the D state. So a really interesting calculation. Then let us move on to quadrupole moment of deuteron. The study of quadrupole moment of deuteron also reveals that deuteron ground state is an admixture of S and D state. That supports the magnetic moment calculation estimation. So this I am leaving as an assignment to you. Just prove that from this study, the values of modulus A square and modulus of B square what you obtain is now nearly same as that of what you obtain from the estimation of magnetic momentum of deuteron. So this is I am leaving you an assignment. You do that. A simple calculation, just follow the mathematics. So that's